Hi, folks. So, last time we talked about the motions of the sky and how the Earth is rotating on its axis, it's revolving around the sun, and it's also precessing on its axis. So, those motions are the reason why the altitude and azimuth coordinate system that we talked about last week doesn't work for star maps because things are just changing. So, what we're going to talk about today is the equatorial coordinate system. And you were introduced this in the lab last week, but now we're going to go through it formally. So, the goal being that you can take any star map and you'll be able to read it and see where things are in the sky. So, let's get started. Okay, guys. So, last time we talked about what was causing the altitude and azimuth to change over time. And that's obviously it's because of Earth's rotation. So, these stars aren't actually moving. Okay, they are moving, but not by much, not by enough that you could see over the course of a night. But so here I've got a star that reached its maximum at 9 p.m. And then a few hours later, it started setting. So its altitude is lower and its azimuth has moved westward for that. So if I want to keep a star map, though, I'm going to have to know its altitude and azimuth at every single minute of every single day. I just can't do that. So we've invented this coordinate system so that we can use it for star maps. Now, for Astronomy 112, most of the things that we're looking at are going to be way out in space, maybe even all the way to the edge of the universe. You're not going to be able to see those with your naked eye. So it's not really helpful to say, okay, go to this altitude, go to this azimuth, and that's where it is. Instead, what we'll normally do is we'll take these coordinates from this equatorial coordinate system that you experienced in lab last week, and then we'll put those in the telescope. And then the telescope will slew where we need it to go. So that's good. We're going to end up using these equatorial coordinates a lot more than we will ever use the altitude and azimuth, just because the stuff we're seeing is too far away. You're not going to see it with your naked eye no matter what. One thing you do need to be able to get out of this equatorial coordinate system, though, is when is an object going to be visible? Is it going to be in wintertime? Is it going to be in the summertime? Is it going to be in the northern part of the sky? Is it going to be in the southern part of the sky? So we'll teach you at the end how to do that. All right, so to develop this coordinate system, let's imagine that all of the stars are painted on this giant invisible sphere called the celestial sphere. They're not. One of the big things I want you to get out of this class is that space is 3D. I'm going to be teaching you some methods for calculating the distance to things way out in space. You may have two stars that look like they're right next to each other in the sky, but in reality, they're like this. They're nowhere close to each other. Okay. But from Earth, it looks like all of the stars are plastered on the celestial sphere. So if they're painted on this celestial sphere, then we've got the Earth then is free to turn inside here. Well, that's what's actually happening out in space. So imagine I'm standing over here on this side. I can see this star right here. I can't see this one. But as Earth turns, as it rotates, eventually it's going to bring me around to this side. This star will have set. I can't see it anymore. And this star will have risen. Of course, the stars themselves didn't actually move. They're still painted on this stationary celestial sphere. Does that make sense? Okay. The other thing is that we can think about dividing the sphere into two pieces using a celestial equator. Now, we have this on Earth too. We have Earth's equator is right here. And so that gives us a northern hemisphere and a southern hemisphere. In the case of the celestial sphere, that's going to divide it into the northern celestial sphere and the southern celestial sphere. Another way you can think about it is if I took Earth's equator and extended it out so that it crosses the celestial sphere over here, then it's going to draw out that celestial equator. And this coordinate system that we're going to be building is based on the celestial equator, and that's why it's called the equatorial coordinate system. All right, so let's imagine that you're standing on the North Pole, like right there. All right, look at your class notes, about 2/3 of the page down. So suppose you're standing on the North Pole. Where would Polaris be in your sky? Pause the video and think about it. Mark it on your sheet. Well, hopefully you can see that Polaris is going to be directly over your head, right? It's going to be at 90 degrees altitude. So drawn this way, Polaris is going to be directly overhead. All right, now imagine that you're standing on the Earth's equator. Okay, that's going to be, so you're like this. Now where is Polaris going to be? Pause the video and think about it. Mark it on your sheet. Did you actually pause? Make sure that you're pausing, guys. This is not a class where you're going to want to just, sit back there and watch and get the information. You're not going to get it that way. This is a class where you need to be actively doing something if you're going to learn the material. So yeah, in this case, Polaris is going to be on the horizon. Do you see that my horizon runs underneath my feet, kind of at a right angle to the rest of my body? So Polaris is going to be right on the horizon there. All right, now let's suppose you're standing in the United States. Now, most of the United States is going to be at about 45 degrees latitude, something like that. Here in Phoenix, we're at 33 and a half north latitude, but let's assume it's about 45. So now where is Polaris going to be in your sky? Pause the video and think about this one. All right, well, you may have been able to logic it out. Another way to think about it is, remember my horizon is going under my feet like this. This is directly overhead. I did kind of a lousy job drawing my person there. But this is directly overhead. This is the horizon. So Polaris is going to be halfway between the horizon and directly overhead. Do you see how that works? Well, now let's think about latitudes. When you were standing on the North Pole, do you happen to know what the latitude of the North Pole is? Well, you can Google it, but it's 90 degrees north latitude. What's the altitude of Polaris at this point? The altitude is also 90 degrees. How about here? What's the altitude of the equator? The altitude of Polaris at the equator is going to be 0. Well, what's the latitude of the equator? The latitude of the equator is also 0. I think you're starting to see a pattern now. If I'm at 45 degrees latitude, then Polaris is at 45 degrees altitude. And in fact, Polaris's altitude is always exactly equal to your latitude. So this is one of the first ways you can access your inner Crocodile Dundee there. If you can never get lost, you can always know what your latitude at least is if you can see the night sky. Remember, I told you that your fist is between 5 and 8 degrees. Here's how you can calibrate that. My screen keeps going dark every time my mouse passes over. Turn that back on, hopefully. There we go. Okay, so look for the Big Dipper. Big Dipper will be in the northern part of the sky. It's visible all night long. These stars are almost exactly 5 degrees apart. So those stars at the end of the Big Dipper are about 5 degrees apart. So hold your fist up and figure out how many degrees there are for your fist. Now these two stars also point to Polaris, about that far. And Polaris comes out, and the Little Dipper comes out in the opposite direction, which you probably won't be able to see, but you might be able to see. So this is Polaris. So that's how you can find Polaris. Now all you need to do is just count up how many fists it is from the ground to Polaris. And let's say that your fist is 6 degrees. If you count up 5 fists, then Polaris is at 30 degrees altitude, which means you're at 30 degrees latitude. So now all you have to do is find out how to figure out your longitude, and which is not hard, but does require a watch. If you're ever interested in that, come see me. That's kind of a separate topic. But at the very least, if cruel astronomy instructor that I am, if I drop you out in the woods somewhere, you don't panic. You just wait for the sun to go down. You find Polaris, count up, see what its altitude is. You pick up your PRC-90 survival radio, which I know you all carried with you, and then you say, hey, yeah, I'm at 30 degrees north latitude. And the rescuers will fly a circle around the Earth. They'll pick you up. You'll be home in time to watch whatever you're going to watch on television. All right, so to make our coordinate system then, we're going to draw lines parallel to the celestial equator. And then we'll draw lines perpendicular to the celestial equator. When you put the two of those together then, you get a grid. And these stars are painted on the grid. They don't move. So their coordinates are always going to be the same. So this distance above or below the celestial equator we call the declination. 0 degrees declination is right on the celestial equator. Then it goes 10, 20, 30, 40, 50, 60, 70, 80, 90. So this would be 90 degrees north declination. This is right at the North Celestial Pole, the NCP. You'll see that some places. Now, we'll call this positive 90 here in this class because that's kind of what we do in the United States, but you should know that to be politically correct, you should probably call this 90 degrees north if you're ever traveling, because otherwise you're seeing everybody in the South is negative, and the Aussies are like, oh, I'm not negative. Mike, what are you talking about, right? So going south then for us here in the United States, it's -10, -20, -30, -40, all the way up to -90 at the south celestial pole. The right ascension then comes around this way. It's that distance around the horizon. And you notice that it's measured in hours. It's not hours of time. It has nothing to do with time. Wipe that from your mind, Padawan. It has to do with distance. It's hours of distance. Oh, yeah, yeah. I know. Every beginning astronomy student hates it. You can too. So I'll explain where that comes from in just a second. So declination is pretty easy. And it's kind of, because it's based on the celestial equator, you just start counting up. Polaris is at +90. So this is the first tip that I'm going to give you. If the declination that you read off the star map is close to 90, then it must be near Polaris. And that means that it must be in the northern part of the sky. On the other hand, if it's close to 0, well, then it's 90 degrees out from Polaris, and so it's going to be over in the southern part of the sky. So a declination near 90 means it's in the northern part of the sky. And also, you know that means it's probably circumpolar, which means it's going to be visible all the time. On the other hand, if it's down towards the southern part of the sky, it's going to rise and it's going to set. Right ascension is maybe a little more complicated, and so I need to give you a little bit of the history of where this came from. The equatorial system was invented by a Greek named Hipparchus. Now, telescopes hadn't been invented yet, so his observatory was really just, a stone wall going around. And he had little marks in it. And what he would do is he would watch when something would rise in the east. And the moment that it cleared the wall of his observatory, he would write down the time. And so he called that the right ascension because it was to the east and it was rising in the sky. So that's where the name comes from and why it's logged as time rather than distance. But I mean, you would think that he would just choose degrees, and that might have been a better way. But time was something that he had available. He could actually log that time with that. So when we're talking about time here, we're not talking about clock time. We're talking about right ascension, distance. So each one of these is about 15 degrees, and you can check that for yourself. Pick up your calculator. Take 360 degrees, that's a circle, divide by 24 hours, and you'll see that there are 15 degrees in each hour of right ascension. So we break it into hours and minutes of right ascension, again, not minutes of time. So there are 60 minutes of right ascension in 1 hour of right ascension. Okay. All right, now we would need to start counting from somewhere. And we got with the declination, that's pretty obvious. We just start counting from the equator. But where do you start counting for these lines of right ascension? Well, we've got the same problem on Earth with lines of longitude. So longitude goes around this way. Right now, our 0 of longitude for the Earth is called the prime meridian, and it goes through a laboratory in Greenwich, England, just outside of London. Prior to this, prior to about 1800 or so, every country had their own maps showing the 0 going through their capital city. But then there was a big conference, and then we were trying to standardize the maps. And as hard as it is for a Navy guy to admit this, at that time, the American Navy sucked. And the Brits had the best Navy in the world. And they said, if you want to use our charts, London gets to be the 0. And that's the only reason why London is 0. They could have chosen anywhere. They could have chosen my house. They should have chosen my house, but they didn't. So we've got the same problem on Mars. Instead, there's a tiny little crater right on the equator that we've drawn a line through. It's called Crater Ares. And we said, okay, that's the 0 of longitude for Mars. The Martians don't like it, but we said, too bad. So you could choose anywhere for this. And this is the second thing that astronomy students have hated for 3,000 years. Hipparchus said, wherever the sun happens to be on March 21st, which is the first day of spring, the spring equinox, that's the 0. And then we'll start counting from there. So, if the sun happened to be here, we'd start counting from here, and this would be 0 and go around. So it's just the way it is. That's just been the tradition. Now, because of precession, where that occurs has changed over time. Originally, it occurred in the constellation of Aries, and so it was called the first point in Aries. That doesn't happen anymore. Remember, the constellations have changed over 2,000 years because of precession, but we still call it the first point in Aries. So there are 60 minutes in each hour of right ascension, and we start counting from that 0. Okay, so to review here, equatorial coordinates, the declination is the distance above or below the celestial equator in degrees. The right ascension is the distance around the celestial equator in hours and minutes. And then these two rules of thumb. We mentioned that if it's near 90 degrees, if the declination is near 90 degrees, it's going to be in the north. Remember, that's the declination. The right ascension tells me when it's going to be visible. If the right ascension on the star map is around 0 hours, then we know it's going to be overhead at midnight in December. If it's closer to 12 hours, it's going to be overhead at midnight in the summertime. So we pretty much usually only talk about summertime and wintertime constellations. Fall and spring are actually a fairly recent invention. Prior to about 1700, fall and spring didn't exist. Those were invented by poets. So when astronomy was created, there was no fall or spring. So we pretty much traditionally talked about winter constellations and summer constellations. Yeah, okay, technically there are ones that are kind of in between. But for our purposes, we're going to stay with tradition. And on your homework and everything we do from here, you're just going to talk about wintertime or summertime. If it's closer to 0, call it winter. If it's closer to 12, call it summer. Okay, so now you know how to use the coordinates for a star map, and you can use that to figure out where things are on the map, where they are relative to each other, and also whether they're the northern or southern part of the sky, and also what season they're going to be available in. For your practice, this time you're going to be working with this star map. This is actually part of the constellation Orion. And that's a constellation we're going to be working with for a lot of this semester. So I want you to kind of get used to it. But if you've ever seen Orion, it's got 2 stars, and like this, and then like this, and then there's 3 stars that form the belt in the middle. Coming down from the belt, you're going to see in your star map, there's actually a stellar nursery. This is where new stars are being born, and we'll be spending a lot of time looking at that. So I want you to get familiar with this. There's going to be some questions that are going to ask you, make sure that you can actually work your way around the star map. And then the last 2 questions, you're going to figure out when is Orion visible and in which part of the sky. So if you've got questions, as always, come see me. I can walk you through this and you'll be in good shape. We'll see you next time.